All right, get ready for a deep dive, everybody, because today we're tackling Alzheimer's research. And let me tell you, the paper we're about to unpack, it's next level stuff. We're talking about a possible link between brain activity and how Alzheimer's, that devastating disease might actually progress.
Yeah, that's right. We're really going down to the molecular level with this one, focusing on this protein, BACE1. It's pretty key in how those amyloid plaques actually form in the brain.
Okay, BACE1, so that's like the villain in our Alzheimer's story, right? But before we go full on detective mode on this research, can you remind us why this enzyme is like the top suspect when it comes to new treatments?
Absolutely. So picture this BACE1 is like a pair of tiny scissors, right? Molecular scissors. And it's snipping a larger protein into smaller bits. Problem is, one of those bits turns out to be amyloid-beta, Aβ, the sticky protein that clumps up into those plaques.
Yeah, those plaques, right? That they're like the calling card of Alzheimer's,
Yeah.
wreaking havoc everywhere. So researchers, they've been trying to block BACE1, basically disarm those tiny scissors, right?
Exactly. But there's a hitch. Baby CE1, it's a slippery character. We don't actually know everything that controls what it does in the brain.
So it's like we've got these scissors and we know they're bad news, but figuring out how to control them is a whole other story.
Exactly. And that is why this research is so fascinating. It's like a whole new lead in the case. It shows us this pathway could be influencing how much BACE1 is made. And get this, it all links back to brain activity.
Wait, brain activity? As in how much our brains are, thinking, firing, doing their thing? That's wild.
It really is. What this study says is that the more active those neurons are, the more likely they are to churn out BACE1. And of course, more BACE1, well, that could mean more of that harmful Aβ we were talking about.
Okay, so now it's sounding a bit like a vicious cycle, right? More brain activity, more BACE1, more Aβ, faster Alzheimer's. That's a bit scary.
It is a concern, no doubt. It makes us really think about how we use our brains and the risk of Alzheimer's, right? But before we jump to conclusions, let's unpack this research a bit. See exactly how they found this brain activity, BACE1 link.
Yeah, let's do it. What'd they find? What's the smoking gun here?
Well, they started with this protein called eIF4B. Now, I know that sounds like a mouthful, but it's a big deal in how our bodies make proteins, protein synthesis.
Protein synthesis. Okay, that rings a bell, but it's been a while since high school bio.
Basically, think of it like this. Our DNA, it's the blueprint, right, for every protein our body needs. Protein synthesis is taking those blueprints and making them a reality.
Okay, so taking the instructions, actually building something. Where does eIF4B fit in?
eIF4B, think of it as the construction foreman. He's reading those blueprints, making sure the proteins get put together the right way, efficiently.
So eIF4B, it's essential, turning those instructions into actual proteins we need. But how does our construction foreman suddenly become a suspect in the Alzheimer's mystery?
That's where it gets juicy. See, the researchers found that brain activity, it influences eIF4B. When neurons are firing, chanting away eIF4B, it's like it wakes up, becomes more active.
Hold on, so the more our brains work, the more active this eIF4B gets. But how does that lead back to our BACE1 problem?
That's the million-dollar question, and that's exactly what they wanted to figure out. They have this hunch, right, that maybe, just maybe, this activated eIF4B was somehow linked to how much BACE1 is made.
So they've got this hunch, more active brains, more of this eIF4B action, but how do you even start testing that? Hook up some brain teasers and measure enzymes.
Well, that'd be interesting, wouldn't it? But no, they went a little more controlled. They used neurons in a dish, like a mini brain in the lab.
Whoa, so they can actually see these neurons firing away? That's wild.
Pretty amazing stuff. So they use this drug. It basically amps up the neuron activity, like giving them an espresso shot, get those synapses buzzing.
Okay, so it's like simulating a super brain in a dish. And I bet I can guess what happened. BACE1 levels went through the roof.
You got it. That's exactly what they found. Way more BACE1 in the neurons with that activity booster.
Okay, so their theory's holding up, but how did they know it wasn't just the drug messing things up? How'd they pin it on eIF4B?
Ah, good point. So they got even trickier. They used this technique to basically silence the gene that makes eIF4B right there in the neurons.
So they like temporarily took eIF4B off the table.
Yeah, exactly. And when they hit those neurons with the activity drug, same as before, well, the BACE1 increase, totally gone.
Wow, so even with all that extra activity, no eIF4B, no BACE1 surge, that's a pretty solid link right there. But this is all still in dishes. What about real brains?
Right, got to see if it holds up in a more complex system. So they looked at mice, especially bred, to show, Alzheimer's-like stuff.
So brains that are already kind of on the Alzheimer's path, what'd they find there?
This was really something. These mice, way more activated eIF4B compared to the healthy mice.
So in brains already dealing with these Alzheimer's changes, eIF4B is going into overdrive. That's got to mean it's playing a part, right? But mice are one thing. What about us?
The big question, right? Does it translate? Get this, they looked at brain tissue from people who'd actually had Alzheimer's compared to healthy tissue.
Okay, no cliffhangers.
Yeah.
What'd they find?
Same pattern. More activated eIF4B in the Alzheimer's brains. Like they found this missing link between brain activity, eIF4B, and BACE1. And not just in mice, in us.
This is huge. This little eIF4B protein, it could be a major player in how Alzheimer's actually happens. But there's still something I'm not quite getting. Okay, brain activity affects eIF4B, which then affects BACE1. But what's flipping the switch on eIF4B in the first place? What's kicking off this whole chain reaction?
That's where our final character steps in, an enzyme called Casein Kinase 2, or CK2 for short.
Uh-oh, things are about to get complicated, huh? Another enzyme, another mouthful of a name. Walk me through it. What is the CK2 and why should we care about it in all of this?
So CK2, it's like the key to the whole shebang,
Yeah.
see, because it's the one that actually activates eIF4B. Does it through this process, phosphorylation. Think of like attaching a little on switch.
So CK2 is what lets eIF4B do its thing, which is boost that BACE1 production. Okay, now I see how the pieces fit.
Right, and the researchers, they figured if we can mess with CK2, maybe we can break the cycle, right?
Yeah.
Stop that BACE1 overproduction.
Now we're talking. So did they find a way to actually block CK2? And what happened? Did it work the way they hoped? So did they find a way to actually block CK2? And what happened? Did it work the way they hoped?
That's the question, isn't it? And they dove right in to find out. They used these drugs, specific ones, that inhibit CK2, like setting up roadblocks so it can't get to eIF4B and activate it.
Okay, roadblocks are up. What happened next? Did it break the cycle?
Get this, it worked. Both in those lab-grown neurons, A and D, in slices of actual brain tissue. Blocking CK2, it meant way less activated eIF4B.
And less eIF4B means...
Less BACE1, exactly. And less of that Aβ causing trouble, like turning down the volume on this whole cascade of things that can lead to Alzheimer's.
This is incredible. We've gone from, like, understanding the problem to actually maybe potentially having a solution. Imagine therapies that go right for CK2 or even eIF4B that could be huge for Alzheimer's, right?
Oh, absolutely. It's a whole new direction for research. Think about it. Intervening early, maybe even slowing down. Who knows, maybe even preventing Alzheimer's from taking hold. But of course, like with anything new, got to do more research, right? We need to know what happens long-term if you inhibit CK2 eIF4B. Make sure it's safe, that it works for people.
Right. Research is a marathon, not a sprint, as they say. But this feels like a huge step, wouldn't you say?
Absolutely huge. And it shows how important it is to keep looking, explore those unexpected paths in research. Brain activity itself linked to this harmful enzyme. It just goes to show the more we learn about the brain, the more questions pop up.
Yeah.
And the closer we get to actually tackling diseases like Alzheimer's.
Totally. And speaking of questions, this got me thinking, if more brain activity can, like, fuel this whole process, right, leading to Alzheimer's, could keeping our brains active in the right ways maybe actually help, like, reduce the risks?
Now, that is a fascinating thought. It's a whole different way of looking at it, isn't it?
Yeah.
Brain activity, not as the bad guy, but as a way to protect ourselves.
Exactly. I mean, we know keeping our minds sharp, brain training, it's good for us as we age. But what if certain activities, actually help regulate these pathways we've been talking about? Keep eI4B and BACE1 in check?
It's a real possibility. And you know what? Researchers are already on it. There's more and more evidence that things like learning a language, playing music, even just being social, it's all good for the brain. Could even build up, like cognitive reserves, make our brains more resilient.
It's like a workout, but for your brain, right? Just like hitting the gym keeps your body healthy. And hey, maybe someday we'll have these like personalized brain prescriptions tailored to our own risks, It's an exciting field, that's for sure. I'm hooked.
Me too. It just shows you how powerful science is, right? Making these discoveries, changing how we think about and how we treat diseases like Alzheimer's.
Couldn't have said it better myself. So there you have it, everyone. We dove deep into the world of Alzheimer's research today, uncovered this potential link, brain activity, and how the disease progresses. But even better, we learned about this awesome research that could lead to whole new treatments, maybe even ways to prevent Alzheimer's down the line. Amazing stuff.
Amazing is right. As we keep unraveling the mysteries of the brain, I have no doubt that there are even bigger breakthroughs just around the corner.
And on that note, until next time, keep those brains buzzing and keep those questions coming.